So today we are having Elisabeth Heifenberger. So Elisabeth did a PhD in Princeton University with Simone Giambich, and then she joined Trinity College as a postdoc this September. And today she's going to tell us about RG interfaces from double-trace deformation.
Is this like a flicker
No, that control that turns on and off this.
Oh, is there? So I just have to use the mouse then.
Yeah.
That's probably awkward for you. So
Just for me.
we do have a pointer which is a stick.
Amazing.
That's okay. I can just do this. Yeah. So, thanks for inviting me. And yeah, I've actually never been to DS, even though I'm just down the road. So it's nice to finally get here. And yeah, I wanted to tell you guys a little bit about the work that I did during my PhD. So I'm working on something slightly different now, but so yeah, the last project I did during my PhD was on RG interfaces. So I wanted to discuss basically what those are and hear about them, and give some background on, so they're a type of conformal defect, which is what I mostly studied during my PhD, and then talk more specifically about RG interfaces caused by double-trace deformations. So first off, what are RG interfaces? So an RG interface is an interface between two theories at opposite ends of an RG flow. So this, like, the operational definition is that it can be created by introducing irrelevant perturbation on half space and then flowing into the deep infrared. So I think this was first done in by Brunner and Rosenkamp in 2007. And then Gayato also had a paper on minimal models, and Kaneshmi has had a lot of papers on RG interfaces. So one thing that is sort of relevant to what I'm going to talk about is this paper from 2015 by Gliazzi, Leandro, Mineri, and Brago, where they considered the ON vector model in D equals 4 minus epsilon. So they started with just the free fields, and then yes.
What is half space?
That is like RD with, it's like a half of RD basically. So it's with, if like you have a Z coordinate where one of the coordinates is greater, it's an infinite half plane.
So only taking the positive.
Yeah, only taking the positive. Yeah. Yeah. So if you perturb this theory on half space with quartic interaction, then flowing to the IR, basically you want to end up at this RG interface where you have free fields on one side and these weakly coupled, like Wilson-Fisher fixed point on the other side. But flowing to the IR can turn on relevant operators localized on the defect. But in this paper, they argued that, well, I think they're right. There's only one relevant operator, which is basically if you take the fundamental field phi, where I haven't talked about the ON model really yet, but there's just phi n scalar fields phi I packaged as a vector. But if you take this to boundary, you can call it phi hat, and the only relevant operator on the boundary would then be phi hat squared, and that can be tuned to 0. So it's reasonable in this case to say like this flows to some RG interface. And they also impose continuity of the derivative with respect to the phi I fields across the interface. So far away from the interface, at d equals 4 minus epsilon, you expect the unperturbed side to behave like a free theory, the perturbed side to behave like the Wilson-Fisher fixed point. So that was just kind of a preview, but then you can say, why are these things interesting? Like, what can we get out of studying them? So first of all, RG flows are complicated, and it's easier to study endpoints of the flows, which are very often CFTs, and operators in the UV get mixed and renormalized to form operators in the IR. So RG interfaces could help us understand how this happens, basically using two-point functions across the interface, which should encode mixing coefficients, which is something Gayato talked about in this paper in 2012. And I haven't written it here, but they also talked about this in the paper, 2015 paper that I just talked about from Liazzi et al.
Sorry, I just want to get the picture clear in my head. You have an interface here between the two theories, and you want to set, talking about the one relevant operator. I would normally think of tuning the temperature parameter, the mass parameter, that's the coefficient.
Oh yeah, sorry, I shouldn't have said tune the operator. I should have said tune the mass parameter. So yeah, like the mass, the coupling is multiplied by that. Renormalized coupling.
Yeah, but it doesn't look like there's a well-defined value of it, because there's one critical value on one side of it, and another critical value which is actually 0 on the other side. So there should be an alternative would be to just put boundary conditions on that field and say that it's a genuine boundary, and the field itself is going to 0 there, which is forcing some additional boundary conditions.
Yeah, so the point with this is that you're having boundary conditions, which, yeah, I guess, so the continuity is in the derivative of the fundamental fields.
Okay, I'm happier with that.
Yeah, okay. So yeah, we're not saying that phi squared itself is continuous.
Okay. Or that the mass parameter itself is continuous.
Yes.
Okay.
Sorry, is the interface sort of like a set of fixed points of the like, I suppose I'm kind of imagining the DCFT as a fixed point of the origin.
So no, it's literally just like a d minus one dimensional like subset of RD.
It's a physical interface.
Yeah, it's a physical interface. Yeah. Yeah. So one reason to study RG interfaces would be to try to see if we can glean some information about UV and IR mixing. And another thing people have mentioned is that if you can somehow create, or if you fail to create an RG interface between two theories that you suspect, like one could be the endpoint of an RG flow of the other side, maybe that could provide like a selection rule, like therefore this theory doesn't flow to that in the IR, but that's kind of like farther off as a goal, I guess. So yeah. I also wanted to say, so since RG interfaces are conformal defects, there's a lot of existing literature related to analyzing defects, and they can be applied to this. Any questions at this point? Oh, I also wanted to mention RG monotones. So this has also been an interest of mine, like throughout my work, and so it can. One reason we would be interested, or like one thing that I find interesting about RG flows is quantities which help make more concrete the idea that RG flows are irreversible in the sense that you expect a decrease in degrees of freedom going from UV to the IR. And the question is, what quantities can we identify that satisfy that? So probably everyone has heard of the C theorem, A theorem, and F theorem, which relate to these RG monotones in the case of 2D CFT or 4D or 3D. And that is in the absence of a defect or with a trivial defect. But you could also have RG flows localized on a defect. So if you keep the bulk at criticality and add a relevant perturbation localized on the defect, then there are also theorems about whether or not there's a monotonic quantity that captures this RG flow localized on the defect. So there's the G theorem for line defects, or the B theorem for surface defects, and the defect A theorem. But then there's not yet a proof of, I think, P equals 3-dimensional defects or P greater than 4 with generic codimension, as far as I know of. The last time I checked, is that?
I think among the students, maybe some have never heard about the C theorem.
Oh, I see. Okay. Yeah. So this is basically the statement that there are quantities which decrease along an RG flow. So the C theorem, for example, is like a linear combination of 2-point functions of the stress tensor. And so that's like the monotonic quantity that was identified by Somolojikov in the 80s to decrease along this 2D RG flow. And yeah, when it comes to defects, well, okay, I guess I should also say there's a difference between even and odd dimensional RG monotones, because in even dimensions, you'll have a Weil anomaly. So in like D equals 4, that is something like the coefficient of the Weil anomaly is what captures this RG monotone. But then in D equals 3, you don't have that. So people have talked about the free energy. So, and then there's like trying to interpolate between these two things. And a similar kind of thing has been proposed for RG flows localized on a defect. So let me see if I have. So okay, one of the monotonic quantities for a conjectured RG monotone for a defect, with a generic defect dimension and codimension, is the expectation value of the defect, which can be thought of like just the partition function, including the defect, and then divided by trivial defect. And that's not actually the RG monotone proposed. So it's this sinusoid multiplied by log of the expectation value of the defect, which is the thing that's proposed to decrease along RG flow. So the statement basically of this defect C theorem is that the UV value of this tilde D is greater than or equal to the IR value. Yeah.
So how did you define your ZD CFT? There's a ZCFT, I'm imagining that's the one on the non-trivial conformal field theory. Your 5-4, your Wilson-Fisher fixed point, for instance.
Yeah.
And you have a Gaussian fixed point at the other end. Mm-hmm. The massless Gaussian fixed point, I think, too. So how are you defining ZD CFT?
Yeah, so in the case of the conformal interface, I would say it gets a little bit tricky because there are like two possible things you could divide by, like either the CFT in the IR or the UV, like on the whole space. So when I talk about like the free energy, yeah, you can basically divide by both of those. But here I was more thinking of like inserting a line defect or something, and then dividing by the theory with the trivial line defect. So
now you'd have the same theory on both sides of the defect.
yes.
Okay, all right.
Yeah.
Now that I understand now.
Yeah, so now that I've talked about like sort of my interest in RG interfaces and also studying RG, like what I'm interested in about RG flows, I want to talk a little bit about conformal defects and some of the sort of technology that we have available. But first of all, I haven't defined a conformal defect yet. So it's a non-local operator that preserves a subgroup of the conformal group. So in d-dimensional space, with p-dimensional defect, the full conformal group is broken from SOD plus 1, 1 to SOP plus 1, 1 cross SOD minus p. So you can sort of think of it as like the conformal group confined to the defect, and then rotations around the defect. I guess that's more if it's a line defect, it's easier to think of it that way. But yeah, that's I've just shown planar and line defects here. And one of the reasons we study conformal defects in the first place is because CFTs are very constraining because of their symmetries, but when we break that symmetry a little bit, it enriches the CFT data while still maintaining enough symmetry to allow for some tractable computations. So it also has a lot of diverse applications in physics. So there's clear physical relevance from like a condensed matter and StatMech perspective, because it could be boundary critical phenomena or magnetic impurities or domain walls. And then as a theoretical tool, D-branes are boundary conformal field theories, where, as I described just now, it can enhance our understanding of RG flows. So currently a very active area of research is in understanding and classifying the phases of defect CFTs. So if you have like a standard CFT and you add a boundary at one point, so you make it end in a conformally invariant way with conformally invariant boundary conditions. So you have a DCFT. You can have a different set of fixed points based on like the couplings that particles have at the boundary versus what you just had when you had a CFT on all space. So one of the tasks for people who study defects is to try to identify new fixed points or phases in the space of defect conformal field theories. And you can also ask, given a defect CFT, how much data can you extract through analytic methods? So one thing that I'll talk about a little bit is conformal bootstrap. So analytic bootstrap applied to defects. But I'll go more into that in a second. And also, what can we say about proposed RG monotones localized on the defect? And can we make any checks of holographic dualities? So when we talk about ordinary CFT data, so I'm guessing most people know this. So we have scaling dimensions that describe how operators change with change in scale, and OP coefficients, which are essentially the three-point function coefficients of operators. So when you bring two operators close together, you can expand them in an infinite sum of other operators at a single one of those points with these OP coefficients. So this is our standard CFT data. But then if we add a defect to the situation, we get these local excitations that emerge on the defect and couple to the bulk operators. So that gives us additional data compared to the theory without a defect. So we still have the typical bulk operator product expansion, where you're bringing two operators in the bulk really close together. but now you can also have the bulk OPE with operators that are localized on the defect. And in addition, you can have a bulk to defect OPE. So as a bulk operator is brought closer and closer to the defect, you can write it as a sum of defect operators with these bulk defect OPE coefficients, which I'll call mu O hat. So then the full set of defect CFT data is given by the conformal, the scaling dimensions of the defect and bulk operators, the defect and bulk OPE coefficients, and the bulk to defect OPE coefficients. So one method that people have used to try to extract these OPE coefficients and scaling dimensions is to use the defect conformal bootstrap. So you may be familiar with the ordinary conformal bootstrap, which uses associativity of the OPE to decompose 4-point functions in 2 different ways. So you can either bring like 1 and 2 close together in that picture, or 1 and 4. And that results in a consistency condition, which allows people to do, well, both analytic and a lot of numeric calculations in like figuring out scaling dimensions and OPE coefficients of operators. But then the bootstrap program for defect CFT is based on the crossing symmetry between the bulk channel and the defect channel decomposition. So in the bulk, you can take 2 operators really close together, and then that sum of operators, if you take that close to the defect, you'll have a bunch of 1-point functions. And in the defect, if you take 2 operators that are on the defect, so you can first take 2 operators in the bulk close to the defect. So you have these 2 different 1-point functions. And then once they're on the defect, take those 2 operators close together. So that's the bulk OPE for the defect, which is a confusing way to say it. But yeah, so basically there have been several developments in recent years regarding this defect conformal bootstrap. I should have updated those references more, but yeah, because people have definitely done stuff past 2017. But yeah, so this is something that is very useful in extracting OPE coefficients and scaling dimensions, especially because often we'll deal with like a perturbative defect where these sums will truncate in some way. So you could like solve order by order in epsilon, for example.
So I mean, the setup you have there,
yes,
works for just a boundary as well.
Yes.
A single boundary.
Yes.
But it would require that the boundary orders at the same time as the bulk. I mentioned that both are critical. In that setup, you can easily have the boundary order at a different temperature or a different parameter than the bulk. So you presume that everything is supposed to be conformal in this one.
You mean on the?
There's a boundary theory as well.
Yeah, so like the line is represented by the operators on the boundary, for example.
Yes.
Yeah, so
that has to be critical as well.
Oh yeah. So that well, yeah, that is a CFT. That's like the definition. That's the, yeah, that has to be conformal. That's right.
That has to be conformal.
Yeah. Yeah. Okay. So now that I've talked about some of the useful things you can get from conformal defects, let's move on to my work on RG interfaces from double-trace deformations. In this paper that we put out last year, we studied what happens when you perturb a large N CFT on half space with a double trace operator. And we used large N methods. So basically the overview is that we use large N methods to compute CFT data, as well as the free energy on a sphere. And we also looked at the holographic tool, which was outlined in this 2017 paper by Melvin Thompson and Schmidt-Conway, where they impose different boundary conditions on either half of the boundary of AdS, and I'll get more into that in a bit.
When you use large N here, you're referring to ON?
Sorry, what?
You're referring to ON, is it?
Oh, and yes.
As a vector?
Yes, yes.
No, it must be a matrix because it's double trace.
No, it's a vector, but it's like, well, actually, it's not just referring to ON. It could refer to other matrix models, but it's like, for example, phi I squared. That's what I mean when I say.
Where phi is the matrix, or
Phi is a vector.
why do you call this double trace?
I mean,
It's just like people tend to call summing over I trace, even if it's not a metric.
yeah,
Yeah, and all these kind of operators.
it's just a convention, I guess. Yeah. Yeah. So we also showed, so in this holographic setup, we showed in this paper explicit agreement between AdS and CFT calculations.
Sorry, it's
Yes.
probably two question, but like, I just, so when you say, I suppose, conformal defect, you kind of like, I mean, I'm, I suppose, used to 2D conformal field theory, and I suppose the defect is the central charge, is it, or, I suppose in that case, is it, and then.
So here I'm talking about like a physical, so usually it's like a subspace. So I'm talking about like an extended operator. So like if you had like a line defect or something, you'd add to the action like something that only depends on one coordinate. So like integrated. So if you have like all of space and then have tau goes to minus infinity to plus infinity. Like this is your extended operator that you're adding to the action. Does that sort of make sense?
Yeah, and then when you were talking about breaking the symmetry group, just in the definition of the conformal defect, what did you say it was going from conformal group to some, sorry, it's,
Oh yeah. Yeah, so it's going to a subset of the conformal group, which is on the defect. So yeah, with a line defect, it's it should be like SL2R, but with like a planar defect or something, this is just yeah, SL3. So cross, if we're in like 4 dimensions, well, let's say we're in D dimensions, D minus 2. Yeah, so it's like the conformal group on the defect itself, and then it's like rotations around the defect. Yeah, so using the setup, we then show explicit agreement between AdS and CFT calculations. So yeah, when I'm talking about these double trace deformations, and like large N theories, I'm thinking about vector models. So we could consider double trace deformations of, like in the ON model, this phi I squared, or in like gross nouveau, psi bar psi squared, which you can argue whether it's justified to call it a double trace deformation. But yeah, and these types of vector models are expected to be dual to Vassiliev higher spin gravity in AdS. So more generically, we could perturb a large N CFT with a double trace operator O squared with a scaling dimension less than d/2 so that it's relevant in the UV. And then you can assume that it has some sensible, the CFT has some sensible large N limit. So we expect large N factorization of the correlators, meaning if you have like a connected k-point function of these single trace O operators, it's suppressed in powers of 1 over n to the k-2/2. And then that means that you can do Wick contractions because the connected part is so suppressed compared to them. So if we're just working like first order in 1 over n, we have these Wick contractions. And then the standard setup for a large N expansion, just to review, is to introduce a Hubbard-Stratonovich auxiliary field, which I'll call sigma. And when integrated out, it gives back the original theory. But then if you, instead of integrating it out, integrate out the fields that the original theory depends on, then you get an induced non-local effective action for sigma. So yeah, this is where the brackets with the O subscript are for evaluated in the SCFT path integral. So yeah, after basically going from the first line to the second line, we're doing this large N approximation we're using large N factorization because we're saying that we can, like the higher order terms, if you look at like the full expansion of this E to the sigma O, those are suppressed compared to this leading, because those are like connected larger. Yeah, so that's the ordinary large N case. And then if we, so in that case, we also, if you'll notice we dropped the sigma squared over 4 lambda because it becomes irrelevant in the higher limit, which is what we're interested in. And at leading order in N, the propagator for sigma is just given by inverting the O propagator in the original theory. So if we then want to create an RG interface, we can add a double trace deformation only on the right half of space. So z greater, if yeah, it like z greater than 0, where one of the coordinates is z. And now we can do the same Hubbard-Stratonovich trick, but we see that in this case, we just get an integral over r plus t. So I should have defined this, but r plus t is just rd with z greater than 0. So I could have just written that. But yeah, so in this case, to get the propagator for the sigma fields, you would have to invert this O correlation function with respect to the original SCFT, but only on half space this time. And inverting something on half space sounds a lot like boundary conformal field theory. So if we use a folding trick to take this z coordinate, which is the coordinate perpendicular to the defect, so take like the UV theory and send z to minus c, then we have a folded picture where we can treat that as a boundary conformal field theory. And in this case, we can use boundary conformal field theory methods, which include like inverting an operator on half space, which was done in this 95 paper by McCavity and Osborne. So we use these techniques to compute the 2-point functions for sigma and O. And we get this as a result. So yeah, the 2-point functions for sigma, O, and then the correlation function between them. So you'll see that like if you take, I also haven't defined this cross ratio. This psi 1, 2 is just x1 minus x2 squared over 4 z1 z2. So you can see that if you take z very large, which is basically going very far from the defect, then 1 over psi will also get very large, and the limit in that case, like this 2f1 will just look like, it will just be 1 basically, and you'll like recover what you would expect for a CFT. So
sorry, I expected the correlator of sigma sigma to be the inverse of the correlator of OO.
yes, that's what this is. But
oh, is it? It is.
Oh, as in it's not like 1 over it. It's
no, it should be an inverse.
Yeah,
as an operator.
Yeah.
So if and you're saying those do in fact satisfy that.
Yes. Yeah, they do.
Okay.
Yeah.
Sorry, I have a very silly question. If we're doing conformal field theory, why do we have 2-point operators? Like I wouldn't interpret them as passes.
Why do we have 2-point, like,
Misunderstanding.
what do you mean 2-point operator, like 2-point functions? So because this isn't a conformal field theory, it's a boundary conformal field theory, so it's like, I was saying that in the limit where psi is large, then it like reduces to what you would expect for conformal field theory, because very far from the defect, you should recover what you would expect for conformal field theory. Does that answer your question?
Just because of the defect.
Yes. Yeah, so we've broken the conformal symmetry. Yeah, so yeah, and there's a bunch of well, the main thing is the dependence on the cross ratio psi. And this was also computed in this Melby Thompson Schmidt Collinet paper, and it agrees with what they obtained. So another thing that we looked at was the free energy on the sphere. So in this case, we had to compactify the theory. So yeah, we started on flat space, but we're interested in the free energy on the sphere because, well, mostly because if you are on a curved space, you can get a Weil anomaly, and then it can tell us something about like the boundary entropy. So we could say something about like the boundary free energy as yeah, in like a certain dimension, and compare that well, we did end up calculating that, although I haven't described it in my slides. But basically, if you look at like D equals 3, because it's a codimension 1 defect, this, yeah, it will tell us about like the B theorem. Which is about this Weil anomaly contribution from the defect basically decreasing along an RG flow. And we did find that that was true, like it was, the Weil anomaly was like smaller in the UV, or sorry, in the IR compared to the UV, but it was a little bit trivial because it was like proportional to -n, I think, in the IR, whereas it's just 0 in the UV because it's a trivial defect. But anyway, that's kind of a tangent. So yeah, the free energy of the large N interface theory, we can think of it as like the free energy of the UV theory plus some contribution from the interface. So the one loop determinant of the sigma path integral. So in the IR limit, this is given by basically minus the log of the partition function of the entire theory divided by Z0 of UV. Where, I mean, we could also define something equivalently with respect to the IR theory, which I think related to your question earlier. So I think that's also a convention that people use, but yeah, this is also something that you could.
So when you breathe on a sphere, what dimension sphere are you choosing? I mean, there's a natural one, which is that all these spaces are, any flat space is conformal to R cross S of D minus 1. So that sphere might be the natural one.
Yeah.
Is that the one you're choosing?
Yes, I think so, yeah.
The Einstein universe.
What?
Otherwise known as the Einstein universe.
Yeah, yeah. Yeah, I think so. For some reason I'm like blanking on this, but yeah. Let me get back to that. So yeah, this F sigma is basically 1/2 log det of G12, where G12 is just the 2-point function of O in the UV theory on all space. So the determinant is only over half space, so we can basically compute this in the usual way that we compute determinants using like by decomposing in terms of like eigenfunctions of the Laplacian. But what we found was easier than doing this on the sphere was because the auxiliary field is only supported on half space, the determinant is taken over the hemisphere, which is Weil equivalent to hyperbolic space. So yeah, we start with so we were starting in flat space actually. So we start with flat space and can rewrite the coordinates in terms of like a cylinder, and we see that it's just related by this factor of z to hyperbolic space HD, which is like the Euclidean version of AdS. So we found basically that it was more convenient to perform the integral in HD. And the result we got for that was this integral that you see here. which also agrees with the holographic result found in this Melby-Thompson paper. And we can take the result that we used from the large N theory and perform some checks using the epsilon expansion for several different vector models. So we can do that for the ON model, Gross-Nouveau, Yukawa, and cubic ON. So without getting into all of the details for those, basically just in the ON model in D equals 4 minus epsilon, we find that the contribution to the interface, or the contribution of the interface to this free energy is given by this function of n and epsilon. And if we take the large N limit, we expect it to agree with the D equals 4 minus epsilon limit of the large N result. So basically, we expect these limits to commute. And we do find that they agree. And the other models also match this expectation, but they're a little bit more subtle. Yeah, now we can talk about the holographic perspective. So in ordinary double-trace deformations, there are well-known holographic results for double-trace deformations corresponding to a change in boundary conditions for a field in AdS. So a scalar AdS field phi with mass m satisfies this relation between the mass and the scaling, the mass of the bulk particle and the scaling dimension on the boundary. Yeah, some CFT operator on the bottom. So there are two solutions to this and two possible behaviors as phi approaches the boundary of AdS. So it could either be like the UV solution that we refer to, which is phi scaling as z to the delta, where z you can think of it as like if we're using Poincare coordinates. Yeah, so we either have the field as it approaches the boundary of AdS as going like z to the phi, or z to this delta, sorry, or z to the d minus delta. And basically the idea of this Melby-Thompson-Schmidt-Collinet paper was to divide the AdS, or the Euclidean version, which is hd plus 1 into 2 halves, and enforce different boundary conditions for each of those halves. The practical way that they did this was if you use Jonas coordinates, basically the way Jonas coordinates work are like the pages of a book, where you can think of the UV theory on if it's like while rescaled, it's on one slice of, or like the front page of the book, versus the IR theory, which is on the last page, and then each slice in between is HD. So if you set W equal to any constant, you'll get HD. Any constant between 0 and 1. Yeah, so in that case, the boundary of HD plus 1 has two HD regions, which are identified with the while rescaled left and right halves of the interface CFT. Requiring that these different boundary conditions are obeyed for different sides basically amounts to solving this solving for the bulk scalar propagator in HT+1 with some mass m, subject to the boundary conditions. So I also wrote the asymptotics for this this bulk correlation function, which is given the name G tilde. So the asymptotics as W approaches 0 or 1. So this variable, there's a lot going on here, but basically as if we have a bulk correlation function G tilde, and we're bringing, this is the W equals 0 and W equals 1. If we're bringing one of the points to, let's say, the W equals 0 side, then this should be a bulk to boundary propagator, which we call K tilde W equals 0. And it should scale as W prime, or sorry, W to the delta over 2.
I think I didn't fully follow your coordinate system that you're using. Can you show it to me one more time? Just
Yes.
Your.
Yeah, I can also write it.
You're calling these, this is Janus coordinate system?
Yes.
Right. Is it the way you're drawing it on the board? It looks like you might be some generalization on Poincare disk.
I think. Well.
So you have a top and a bottom point, and up in the right hand corner of transparency, you have a disk.
Yes.
And the two meet at 2 points on the disk.
Yes.
So it looks like a Poincare disk.
Yes. So it's the same space, it's just different coordinates. So yeah. So the way I've drawn it.
Boundary space is your original space. So because you added Z as this yes.
Yes.
So you've got a half space on that boundary.
Yes.
Yeah, and they must meet somewhere. Yeah. Okay.
Okay. Yeah, I'll just finish writing this just for reference. Okay, so we have this asymptotic behavior for G tilde, which tells us, this is basically what we require of G tilde. So it has to solve this equation for a bulk scalar in the bulk, or sorry, a scalar in the bulk with these asymptotics, and what they do in the paper is reduce this problem to solving for K tilde. So yeah, I haven't written what they actually found for it, but it turns like their final result was for this K tilde to be 2 of 1. So essentially what we did was look at this K tilde and try to understand, so if we compare calculations using Witten diagrams of different, say, 1-point functions, it would correspond to a tadpole Witten diagram, for example, like a 1-point function in the CFT should correspond to a tadpole Witten diagram. And if we specifically want the 1-point function of O, which is associated with the IR side, it should correspond to a tadpole Witten diagram. Which ends on the W equals 0 side. And if we wanted the 1-point function of sigma, it should be it should correspond to a typical Witten diagram, which ends on the opposite side. So we basically looked at 1-point functions, 2-point functions, and 3-point functions of these O and sigma, combinations of O and sigma, and we compared them to what we should expect from the Witten diagrams. And we found that they were equivalent using identities which relate the bulk propagator and bulk to boundary propagators for phi, the bulk phi, to a convolution on the boundary, which I've tried to represent pictorially using this this k tilde going to the w equals 0 side is equal to the original, or like the k delta, which is if both sides were the IR theory, sorry, both sides were the UV theory is k or k delta. And k d minus delta would be if both sides were the IR theory. And so we can basically relate a bulk to boundary propagator if it's a homogeneous space boundary to if we have these mixed boundary conditions using identities such as this one, where we have the original k delta propagator and then we're subtracting some convolution of k delta going to the other side convolved with this O sigma on the boundary. Does that sort of make sense? Okay. Yeah, so that's basically the gist of what we did to show equivalence of AdS and CFT. And yeah, so just to summarize, so what we did was to compute various DCFT data and as well as the free energy on the sphere, and we found manifest agreement with AdS calculations for 1, 2, and 3-point functions. And in terms of future directions, there are a lot of things you could do. Well, the most obvious thing is just to compute additional DCFT data. So I didn't list all of the data that we computed, but we computed 1-point functions and some OPE coefficients, and we also computed various things in the ON d equals 4 minus epsilon perturbative interface. But yeah, there are a lot of other things you could compute, like 3-point functions, and as well as the coefficient of the 2-point function of the displacement operator, which I didn't discuss, but is essentially a protected operator that occurs when you have when you break translation invariance, you still have this displacement operator, which is conserved. So, okay, another thing is to investigate the stability of the interface under different RG flows, either localized on the interface or taking place in the bulk. I mean, one very simple thing you could do with the interface is if you didn't tune this like a mass term to 0, if you didn't tune the mass of like a defect mass term to 0, and you looked at the flow of this term, you could end up with just essentially 2 disconnected paths, or 2 boundary conformal field theories, which have no overlap. So the O sigma 2-point function would just be 0. But yeah, it would be interesting to think of different RG flows that you could consider either on the defect or taking place in the bulk. And another thing is the mixing of UV and IR operators. So I discussed that a little bit in the beginning, but so I didn't talk about how it was computed by Gliazzi, Leando, Mineri, and Rago in this d equals 4 minus epsilon interface ON model. But they were able to compute some of the mixing coefficients for that compare the IR operators to the UV operators. And it's actually a lot trickier in the large N case because in the 4 minus epsilon case, you have truncation, like epsilon.
By this you mean your mu O prime coefficients?
Mu O prime.
Your slides.
I'm not talking about the bulk to defect OP coefficients. I'm talking about if you had like operators in the IR, and you expected them to be sum over renormalized operators in the UV with some coefficients. I'm being really schematic, but let's say you have like nearly degenerate operators in the UV, and they combine in some way to form the IR operator. Like, how do they mix? So they, in this Gliazzi et al. Paper, were able to sort of get some of these coefficients, I think, but it's a lot easier to do in the 4 minus epsilon case compared to large N because, well, they use the fact partly that 1-point functions there's only one 1-point function that I can't remember now if it's order epsilon, I think. So essentially they get like a truncation in the expansions that they're looking at in terms of epsilon, but we wouldn't be able to get the same thing at large N. But yeah, I haven't described it very precisely, I'm sorry about that. But it would be interesting if we could try to figure out like how to understand the mixing at large N. So yeah, with that, thank you very much for your time and attention.
Sorry, what were some of the other field theories that you mentioned? O and U.
Yes, so I kind of glossed over those, but they are, yeah, so they're like the gross nouveau Yukawa model has also a scalar. So it has this term, and I think it also has a 5-4 interaction of the scalar, if I remember correctly. But the reason why I mentioned that, yeah, you might ask, like, why am I talking about that if I'm talking about double trace deformations? Let me just write out the whole thing. I think this is it, unless I'm missing something. But yeah, so this is not a double trace deformation in how we're defining double trace deformations. But the gross nouveau Yukawa model at d equals 4 minus epsilon, and the gross nouveau model, which does have clearly have a double trace deformation. Let me write that as well.
Probably you have the kinetic term for S as well, do you?
Oh yeah.
Yeah, no, that's okay. And you, yeah.
So So the gross nouveau clearly has this 4 Fermi interaction, whereas gross nouveau Yukawa only has 2 fermions, like the Yukawa term. So the gross nouveau though at d equals 2 plus epsilon and the gross nouveau Yukawa at d equals 4 minus epsilon are in the same universality class. So that's why we care about the gross nouveau Yukawa, because basically we can provide a check of our formula for this f of sigma, this large N formula. But we have to sort of be careful because the way we defined this, like the gross nouveau Yukawa, the version of it where we have this interface, the question is, what do you do with the extra scalar, basically? So we can basically, long story short, we can like use gross nouveau Yukawa as a check of this f sigma term in another dimension. Even though you could say we already checked d equal 4 minus epsilon in the ON model, but also we have another dimension of the double trace operator. So we should just use the same dimension as the double trace operator of the GN model because they're in the same universality class. Anyway, there's a way to go from this GNY model to a check of the f of sigma of delta, where that's the single trace operator O. And yeah, it's a little bit nuanced, like how we actually go from one to the other, but yeah, does that sort of answer your question?
Yeah. And if that delta it would be some, like it wouldn't just be the same delta with bosons. Would you need another scaling parameter from, say, fermion to fermion?
So this would be the UV theory. So for the fermions, the 4 Fermi interaction, our O that I was talking about would just be psi I, psi I. So that would be, the scaling dimension should just be 2 times d minus 1 over 2, which is what you would have for free fermions. So it's just equal to d minus 1. So yeah, if we wanted to plug in delta equals d minus 1, d equals 4 minus epsilon, then we could find our way back to G and Y.
Do we allow d equals to 2, or it should be at least 3 in these considerations?
Yeah, you could have,
Or
well, it should be,
safety must be,
sorry, what?
like what dimensions safety you consider?
So we would consider, for like the gross nouveau, we would consider d equal 2 plus epsilon. So yeah, the fixed point would be perturbative in epsilon. So you wouldn't want to have exactly d equal 2, but d equal 2 plus epsilon.
But then just more general question, can you generate like any new insights about like just dimensional well-known safeties like in your small
So
example in AdS CFT, like you have 2 DCFT, 3 AdS.
yeah, I think it's, so part of the motivation was to try to understand things in like, so a lot of RG interfaces have been in like 2 dimensions, and to understand how it would play out in like generic dimensions. And yeah, so it's more like we're using these well-known CFTs as a testing ground rather than we're trying to like find something new with them.
I think you would mostly be interested probably physically in epsilon equals 1. Which,
oh yeah, that's true.
So then 3, or what was this? 4 minus 4.
which you get 3 in 2 different ways.
Yeah. Yeah, the most physically interesting thing would be 3 dimensions. So
Yeah, I'm just asking because mathematically DCFTs, at least for me, are the most interesting. structures, especially when you consider relations to modular forms and topology they appear in DCFT. But I have very little understanding of time dimension. Thank you.
How do you think this generalizes to non-double trace operators? Is it direct, or are you using too many methods relying on the fact that it's double trace?
Oh, non-double trace.
Yeah, I'm sure it's something more complicated than double trace.
Yeah, I think. Yeah, I think I'd have to think about all the assumptions that go into it. So I'm not sure, but I would guess that it's not very generalizable to non-double trace, but
You're thinking of a single trace or a the
Yeah,
forward
more
coupling within a layer.
complicated, like the one that is called hypercubic,
Yes.
where you have something that is just phi I to the fourth, but it's not really phi I to the fourth. This is not double trace. It's a model that people like.
Just add this is probably a bit. I was just wondering about the metric for the Janus or the Janus metric. So you're saying W goes from 0 to 1,
yes.
and when it goes to 1, it's singular, is it?
Yeah, so it's not, so W equals 0 and W equal 1 are not included, like,
Okay.
yeah.
Oh, sorry, it was, sorry, random brackets. Yeah, so that anything between 0 and 1, not included 0 and 1.
Yes.
You're saying it's like a book?
Yeah, I think of it that way because it's like each slice, like each choice of W between 0 and 1 gives you a copy of HD.
I see it.
Other questions? Okay. Thank you, Isabella.